Hello friends, welcome to MOL-MENTUM. So today we will discuss the graphical representation of variation of molar conductivity with concentration, and then we will discuss about Kohlrausch law. I think this question is going to be important for this year's 2026.
Okay, so let us begin. So on this axis we have delta C means concentration, and on this side we have molar conductivity lambda m. So suppose we have two different electrolyte. So weak one varies like this. So this is for weak. We can take any weak electrolyte like CS3COOH or any other carboxylic acid. Then in case of a strong electrolyte varies linearly like this. So a strong one like we have KCl, NaCl, etc. Now the question is why there is difference in variation of these two electrolytes. Okay, so as we see, this axis is of concentration. So when we move towards origin, that means we are decreasing concentration. So concentration is decreasing. Concentration decreasing means what? We are adding more and more solvent into it. That means volume is increasing. That means this is called dilution. It means upon dilution, when we approach towards origin, means when concentration decreases, there is a significant increase in concentration of weak electrolyte, but no significant increase in concentration is observed in case of strong. So this thing you have to understand. Why no significant increase? Because KCl is a strong electrolyte, or any other electrolyte, you can take NaCl, HCl, anything. So strong means their alpha is nearly equals to 1. That means even if we add more solvent into it, that means even if we dilute it, since alpha is nearly equals to 1, that means they almost dissociate 100%. So there will be no significant increase in molar conductivity. Molar conductivity is because of the ions, whereas in weak electrolyte, so when we dilute it, so basically ionization is going to be there. So a more number of ions are there, and which causes the sharp increase in molar conductance. Okay, so this is the variation that we should know. A strong one varies linearly, whereas weak electrolyte varies. It forms a curve, basically. It increases sharply. Okay. Second observation is, in case of weak electrolyte, look at this point. Wait. Look at this point here. So after some time, even if we add more amount of liquid or solvent into it, this axis, green line, is going to be parallel to the y-axis. That means it is never going to meet. What does it mean? It means alpha for weak can never be equals to 1. It can never be 1. That means weak electrolyte can't be dissociated up to 100%. Okay, that means since weak electrolyte can't be dissociated to 100%, that means we cannot determine about total means dissociation of ions, total product of ions, what we determine in equilibrium chapter of class 11. So for that only we have Kohlrausch law. Kohlrausch law for the means independent migration of ions. So what is Kohlrausch law? Kohlrausch law is, it states that the limiting molar conductivity of an electrolyte can be represented at the sum of the individual ions. So if I represent limiting molar conductivity lambda m infinity, so it is represented as the product of each ions, lambda m of positive plus negative, and then lambda m of negative. What does it mean? It means when we sum the product of the ions of weak electrolyte, then we can calculate means lambda m infinity. This is called limiting molar conductivity. This term is very important. Limiting molar conductivity. In simpler words, we can say this also means molar conductivity at infinite dilution. Infinite dilution means when we add too much of water, this point. So basically there occurs a point when beyond which it cannot be diluted. So basically a point where these weak electrolyte can't be diluted beyond that point, then it is called that limiting molar conductivity, or the molar conductivity at infinite dilution. that means beyond which dilution is not possible. Okay, KCl, it can be, means KCl can be extrapolated to y-axis, and then we can get this point as limiting molar conductivity for a strong one. But for weak we can't determine, because these two are never going to join each other. So for that purpose only we have Kohlrausch law. So Kohlrausch law says it is the sum of the ions. Is it clear? So again, if I take any example of calculation of lambda m, so again I can take the same example, like how can we calculate molar conductivity of weak electrolyte at infinite dilution. So if I take any weak electrolyte like CS3COH, so when CS3COH dissociates, it forms CS3COO minus plus H plus, but there is equilibrium. So since we all know that alpha for weak acid is generally 5 to 10%, 5 to 10, that means it dissociates only 0.05 to 0.1. Okay, so how can we calculate this infinite dilution, means how can we calculate the product of its ions when it is 100% diluted, which is not possible. Means we have to calculate the ions product of some of these ions at 100% ionization, which is not possible. So for that only we have Kohlrausch law. So Kohlrausch law says we can calculate lambda m for CS3COOH. This is lambda infinity. So it says we can calculate lambda infinity using sum of these two ions. So CS3COO minus plus lambda infinity of H plus. Now since this acid can't be diluted to 100%, so that means we can take these two ions from any other component. So we can take a strong electrolyte. How can we add these one? Like if I take lambda m infinity of CS3COO minus plus, now if I take any strong electrolyte, like I can add lambda m infinity of Na plus. So basically I'm assuming NaCl here, because NaCl is a strong electrolyte, it dissociates 100%. So I will add these two ions. So I have added what, Na plus, so write it in one bracket, then I can write lambda m lambda of H plus. Okay, so since I'm taking NaCl, so I will subtract this value, or you can also add this one, add these two, so it will be lambda m infinity of Cl minus in second bracket. Then in third one we can write, we can subtract this one, because we have added Na plus, we have added Cl minus, so we will all together subtract NaCl. So we are adding Na plus and Cl minus, and now we are subtracting Na plus and Cl minus. So I will write Na plus plus lambda infinity of Cl minus. Okay, so basically look at this point, we have added Na plus, we have added Cl minus, and at the same time we are subtracting Na plus Cl, and that means there is no change in the equation. Now the thing is, why we are doing this? Because we know when we write them all together, like this one, so again CH3COO minus and Na plus, so it forms what, CS3COO Na. It is a strong electrolyte, not plus, it is a strong electrolyte. Again these two HCl, it is also a strong electrolyte, and then we are subtracting what, NaCl, it is also a strong electrolyte. So this is the application of Kohlrausch law. That means using strong electrolytes we can calculate the lambda m infinity of weak one. Okay, fine. So there are several questions in NCERT also, which we can take. One more thing that you should note from here is relation between degree of dissociation, that is alpha, and lambda m infinity. This is very important. So basically alpha is what, degree of dissociation. So degree of dissociation relates to means molar conductivity at any concentration, then molar conductivity at infinite dilution. Second relation that you should know, it is again from class 11th equilibrium. This is the equilibrium constant K, or dissociation constant K. So K relates to alpha like C alpha square upon 1 minus alpha. So these two relations are important to solve any numerical. Okay, so even in this chapter, we have one question in NCRT in which we have to calculate lambda m for any acid using Kohlrausch law. So we have one question in this chapter in which where we have to apply lambda m, and this question is I think is going to be important for this year board exam.
Like this question is important. Using Kohlrausch law, calculate lambda m infinity of water. So how can we calculate lambda m infinity of water using Kohlrausch law? So basically Kohlrausch law says that lambda m infinity of water is going to be the sum of the product of its ions. That means lambda m infinity of H plus and lambda m infinity of OH minus. So how can we calculate this using Kohlrausch law? So since water
Neutral compound means weak electrolyte, so we can't associate it to 100%. So basically, how do we calculate this is we can write lambda m. Yeah, I should write lambda infinity of H plus, then we can write lambda infinity of Cl minus, because basically I'm adding this HCl and NaOH. First I will add HCl NaOH, these two are to be added, then I will subtract NaCl. So when I add HCl NaOH, what we are getting? H plus, Cl minus, Na plus, OH minus. And the moment I subtract Na and Cl, so that means these two are being removed, Na and Cl. So what we are left with is H and OH. That's what we need, H and OH. Okay, so I will add H plus, Cl minus. Then in second, I will add lambda m infinity of Na plus lambda m infinity of OH minus. Why we are doing this? Because these are strong electrolytes. So HCl is strong, NaOH is strong. Then in last step, I will subtract lambda infinity of Na plus and lambda m infinity of Cl minus. So basically, when we are adding these two, we are getting HCl. When we are adding these two, we are getting NaOH. And when we subtract this, so we are subtracting what? NaCl. NaCl. So Cl gets subtracted. So this one is eliminated. In NaCl, Na gets subtracted. It is eliminated. So what we are left with is H and OH. So basically, using this Kohlrausch law, we can find lambda m infinity of any weak electrolyte taking what? Strong electrolytes. These are strong one. HCl, NaOH and NaCl. All of them are strong and they dissociate 100%. So this is Kohlrausch law, means to calculate lambda m infinity of any weak electrolyte by taking the ions from a strong one, because they are ionizable, and for them alpha is nearly 1. Thank you.